Alright, we're going to keep going with variations on bullets and targets. So here we have the same bullet traveling, V1I, traveling at 300 meters per second. Again, using to the right as our positive x value. This time, the target is moving toward, which we saw before. It's -5 meters per second. The bullet, in this case, though, keeps going. It passes through, but when it passes through, it slows down. And that's V1F. And so that's positive 150 meters per second. And then the target, we don't know. It's hard to say which way the target's going. So we don't really know the direction, but we can calculate and we'll find out whether that's a positive or a negative value. So M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. In other words, the initial momentum equals the final momentum. And we fill in values. So we have 5 grams times 300 meters per second plus 500 grams times -5 meters per second is equal to 5 grams times 150 meters per second plus 500 grams times V2F, which is our unknown. And so we simplify this down, and we get -1750 gram meters per second equals 500 grams times V2F. So, did a few algebraic steps at once there, but I'm sure that you'll be able to manage to put this all into your calculator. It might take you a couple more steps, and then you can get down to this point. And you will find out that V2F is -3.5 meters per second. So the target was moving to the left at 5 meters per second, and then it slowed down, but it was still going the same direction. Alright, now the bullet bounces off, and so we've had a lot of the ones where the diagram was on the slide, but it actually wasn't in your packet, and so you would have had to have been drawing the diagrams for each of those, although I imagine many of you weren't drawing the diagram. If you see one of these problems on a homework, a quiz, or a test, guess what? You better draw the diagram. Alright, so initial, we've got a bullet. Now, why are all these problems so similar? Why do they all have a bullet traveling at 300 meters per second, the bullet's always the same size, and so on? Well, that's to make it simple for you to be able to focus on these different cases. So we can go through and you can see how the sign changes. Sometimes V2F equals V1F and sometimes not. Just all these different possibilities, bouncing off, going through, etc. Alright, so this one, oh, that's not final. This is all initial. V2I is equal to 0. It says it's a stationary target. And then the bullet bounces back. So in our final state, we've got our bullet coming back. So V1F equals -150 meters per second. Again, sticking with our positive x direction, being to the right. So the bullet's going to the right there. And our target started off stationary, so it must be going to the right. V2F is our unknown, and that is our final state. Really important to label the initial state and the final state. Important to have a diagram to show what your positive direction is, show what your knowns are, show what your unknowns are. Okay, like I said, this is the first time where I'm fully drawing the diagram, but on all those other ones, I annotated it, I put my positive x direction, I labeled initial and final. You need to do that on all of them. And then when you go to do your solution, what do you start with? You start with an equation from the equation sheet. Don't just start 2/3 of the way to your answer. No, start with an equation on the equation sheet. Write it down how? Symbolically, that's right. Okay, once you get the symbolic equation down, that's when you go through and substitute things in. You can mark that out because that's 0. And so you go 5 grams times 300 meters per second equals 5 grams times negative 150 meters per second plus 500 grams times V2F. All right, so we get 1,500 gram meters per second equals negative 750 gram meters per second plus 500 grams V2F. All right, and then we get 2250 gram meters per second equals 500 gram meters per second. Oh, not gram meters per second, just 500 grams times V2F, which will be measured in meters per second. And we divide by 500 on both sides. And 2,000 divided by 500 is 4, so we know this is going to be a little bit bigger than 4. So V2F, and if you're really careful, you put vector hats over all of those because that is the vector form. We're not just solving for the magnitude like we do for forces in the second law, but here we're actually solving for this vector quantity. And so it'll have a positive or negative sign depending on the direction, and it comes out to 4.5 meters per second. Sorry, it's a little messy. I'm still mastering this pen and trying not to go too slow with it. All right, now we move on to collision types. All right, so collision types, you can read about those in the textbook. And I just want to point out a few things. Let's see. Okay, just wanted to see how much space I had. So I have the full slide. So there are really elastic collisions, and there are inelastic collisions. Okay, and those do not overlap. It's either elastic or inelastic. Okay, all collisions are either elastic or inelastic. Now, there is this third type. However, it's just a special case, and it occupies a little section within here. We'll say, all right, well, within here, perfectly inelastic, but it falls squarely within this bigger category. Okay, it's not a third type, really. It's just a subtype. Okay? There we go. All right. Now, elastic, kinetic energy or mechanical energy, and it's said differently in different places, but you're either saying that the kinetic energy is conserved or the mechanical energy is conserved. And for elastic collisions, for all of this whole category, kinetic energy or mechanical energy, not conserved. Okay, and these are just two different ways of saying the same thing, kinetic or mechanical. Okay, and so that means for inelastic and perfectly inelastic, energy is not conserved. Okay, now for all of these, momentum is conserved. Okay, momentum's always conserved. Now the only thing different about perfectly inelastic is that the objects stick together. Alright, that's hard to see, I know, but I just said it, so hopefully you're able to hear that. The objects stick together. Okay? So inelastic, they may or may not stick together. If you look at this, there's this whole big area here where they don't stick together. Okay, here and here. So all that don't stick together. And then there are also these perfectly inelastic where they do stick together. All right, but no matter what the type of collision, momentum is conserved. All right, so let's take a look and review all of our collision information, summarize it here, make sure everybody's perfectly clear on all of this. If two objects move apart after the collision, does that mean it is elastic? Okay, fill in your answer. These questions are in your packet. How can you tell what type of collision you have? Okay, and the choices are elastic, inelastic, or perfectly inelastic. Okay, but really it's you're elastic or you're inelastic, and then if it is inelastic, then yeah, it's good to know if it's perfectly inelastic. So how do you know? Write down what you think the answer is. In which of the three types of collisions is momentum conserved? So you have these three choices, or you could do two of them or three of them, whatever. You're going to fill that in here. And then finally, in which of the three types of collisions is mechanical energy conserved? Or you could say internal kinetic energy. All right, so I want you to fill in the answers to all of those, and then we're going to go over these questions in the next video.